Welcome back to the deep dive. This is where we take that huge pile of research you send us, all the articles, the technical papers, the proposals, and we really drill down to the core ideas.
And today, we're looking at something truly massive.
We really are. We're not talking about market trends or, some forgotten piece of history. We are looking at what might be the single most audacious engineering proposal ever conceived.
I think that's fair to say.
We're talking about how humanity could fundamentally reshape the most hellish planet in our solar system, Venus.
It's a radical vision. We're diving into a concept from this proposal, centennial collapse, a cascade engineering model for Venus terraforming. And it just completely challenges the conventional wisdom that this kind of planetary transformation has to take, thousands and thousands of years.
Okay, let's unpack this right away, because for anyone who hasn't really looked at our neighbor planet, the scale of the problem on Venus is it's staggering.
It's a thermodynamic nightmare, really.
Exactly. We're talking about a surface hot enough to melt lead. That's around 450 degrees Celsius. And the atmospheric pressure is 92 times greater than Earth's. I mean, the air itself would crush you.
And that air is almost entirely carbon dioxide. 96.5%. It's the literal definition of a runaway greenhouse effect, locked in this incredibly stable, hot, high-pressure equilibrium.
That's the crux of it, isn't it? That's stability. Because the old proposals, the traditional ones, they basically said, look, we just have to wait.
Right. We need 1,000 years, minimum, just for the planet's internal heat and all that atmospheric thermal load to passively radiate away into space.
But the ambition in this source material, it takes that 1,000-year timeline and just crushes it.
It compresses it to about 1 century, a single century for a total planetary transformation.
1 century, that's the lifespan of a modern nation, not a solar system. What is the fundamental shift in thinking that even makes that seem possible?
It all comes down to the physics, specifically forcing mechanisms. The core insight is that, yes, Venus is in a stable equilibrium, but if you apply a massive, coordinated, and continuous push,
The perturbation.
a very carefully designed perturbation, yes, that system has to destabilize. It must cascade toward atmospheric collapse and escape. It's controlled, systematic planetary destabilization.
So we're not talking about sending up giant atmospheric vacuum cleaners to slowly suck the air away.
No, not at all.
We're talking about engineering a complete flip of the planet's entire thermodynamic state by kind of pushing it until it falls over.
Precisely. We're moving away from brute force removal and into exploiting its inherent instabilities. So our mission in this deep dive is to explore the 6 integrated systems that, when you layer them together, achieve this self-reinforcing transformation.
And they work multiplicatively, right? Each one makes the others more effective.
That's the key to the whole model.
Okay, so let's start with the biggest pieces on the board. The primary forcing mechanisms, the things that provide the continuous energy and, I guess more importantly, the thermal gradient needed to kick this whole thing off.
Right. And the first and most monumental is the orbital mirror system.
This is the engine of the whole project.
It's the continuous driver. And it's engineered for a really critical dual purpose. It has to cool one part of the planet and superheat another at the same time.
And that action is what creates the massive temperature difference, the gradient that you need to get the atmosphere moving.
Exactly. It has to overcome the incredible inertia of that thick atmosphere.
Okay, let's start with the cooling side of it. We are talking about an array of 40,000 individual mirror elements?
40,000, yes.
Yeah.
And each one is 500 meters in diameter.
Half a kilometer each. And where do you put something like that?
They're positioned at the Venus L1 point. For you listening, the L1 Lagrange point is that sort of gravitational sweet spot between Venus and the sun.
Where the gravity from both of them kind of cancels out, so an object just stays put.
Stays put, exactly. It remains perfectly positioned between the sun and Venus, which is exactly where you need it to cast a permanent shadow.
And the size of this shadow, 40,000 of these things. This is a huge structure.
Oh, it's colossal. The array is engineered to block 30% of all the solar radiation that would normally hit one entire hemisphere of Venus.
30%. Can you put the amount of energy that is into perspective?
I can try. The total power intercepted is 3.5 times 10 to the 17th watts. To give you some context for that number, the total energy consumption of all of human civilization right now is around 18 terawatts.
Okay.
That's 1.8 times 10 to the 13th watts. So this array intercepts and redirects nearly 20,000 times the energy used by every person, every factory, every city on Earth.
Wow. That is That is a truly staggering scale of energy management. And the immediate goal of blocking that much sunlight on one pole is what?
The goal is to create a polar cold trap. You drop the local temperature, you insulate that whole hemisphere from the sun, and you make it possible for the carbon dioxide atmosphere to finally get cold enough to condense,
Just now. Wow.
to precipitate out as solid COO ice, dry ice. You're effectively creating a massive permanent ice cap on one side of the planet, sequestering the atmosphere itself.
So one pole is perpetually dark and freezing. But, he said as a dual-purpose design, the opposite pole is being aggressively heated at the same time.
Exactly. This is the magnification array. It's even more focused. It's made of 10,000 parabolic mirrors, and these are even bigger, a full kilometer in diameter each.
And they're concentrating the sunlight that isn't being blocked onto the other pole.
They are. The source material says this concentrated radiation reaches 10,000 times the normal solar intensity.
10,000 suns focused on one spot. What kind of temperatures does that create?
Surface temperatures over 2,000 degrees Celsius. We're essentially turning Venus into a massive, unevenly heated planetary scale engine. It's driving a colossal thermodynamic cycle.
I think we can all grasp the raw power of that heat and cold, but why is this extreme temperature difference, this critical gradient, so fundamentally important to the whole plan?
It's all because of the atmosphere's density. If the air were thin, like on Mars, the heat would just radiate away. But you have 92 bars, this thick, viscous atmosphere. So when you impose a 1,500-degree temperature difference between the hot pole and the cold pole,
You get huge pressure differences.
extreme pressure gradients. We're talking about pressure changing by about 100 pascals for every kilometer you move horizontally.
That sounds small, but I'm guessing over a planetary distance that generates unbelievable winds.
It creates sustained meridional circulation winds flowing from the hot pole to the cold pole exceeding 500 meters per second.
500 meters a second, that's roughly 1,100 miles an hour. That's faster than any hurricane on Earth.
Much faster. For you listening, that's about half the cruising speed of a modern jet airliner, but it's a continuous, planet-wide wind system.
Wait a minute, 500 meters per second. Venus already has its super rotation, which is fast, but that's only about 100 meters per second. This is 5 times faster.
And that is the crucial difference. The natural superrotation of Venus is a stable, frustrating equilibrium. This engineered circulation is a continuous, violent, forced convection. The mirror gradient provides that constant energy that prevents the atmosphere from ever settling back down after it gets hit by the next system.
Okay, let's take a deep breath, because the next system is those episodic energy shocks.
Mm-hmm.
And this is where it gets really interesting and maybe a little frightening.
Mm-hmm.
We are talking about ultra-high-yield thermonuclear devices.
This is where we go way beyond military-grade yields and into, well, planetary engineering yields. And this concept actually has some historical roots, which the source material points out.
Right, this isn't totally out of the blue.
No. Edward Heller, back in the 1950s, the father of the hydrogen bomb, he was already exploring concepts like Project Sundial. They were looking at devices that could theoretically yield 10 gigatons.
And that was all based on the Teller-Ulam staged fusing design.
Correct. The principle is both elegant and terrifying. The radiation from a small initial fission or fusion stage is used to compress and ignite a much larger secondary fusion stage. And the physics itself, it doesn't really have a fundamental upper limit. It's all down to engineering and logistics.
And the proposal here says those engineering constraints have been pushed far beyond that 10 gigaton baseline.
Absolutely. The multi-staging principle is scalable. So a 3-stage device gives you your 10 gigatons. But the analysis suggests a 4-stage device is viable for 100 gigatons.
But that's not even the end of the line.
No. The proposal relies on the ultimate configuration, the 5-stage design. And that is the 1 teraton device, 1,000 gigatons.
The Terraton shock. Just saying the name, it sounds like something from mythology. It really forces you to rethink the word weapon.
It's not a weapon. It's more of a directed catastrophic force. Let's try to quantify that energy for you because it's hard to grasp. A single 1 teraton device releases 4.18 times 10 to the 22nd joules.
And why should that number mean anything to us?
Because it's getting close to the estimated kinetic energy released by the Chicxulub asteroid impact.
The one that killed the dinosaurs.
The very same. That was estimated at around 10 to the 23rd joules.
So we are talking about creating artificial extinction-level energy events, but aiming them for constructive planetary engineering. The sheer audacity just to propose that is astounding.
It completely shifts the conversation from human conflict to really applied planetary geology. But the raw energy release is only half the story. The other half is how that energy interacts with Venus's unique atmosphere.
Right. How does that kind of extreme energy couple with a 92-bar atmosphere?
This is the critical part. Because the atmospheric density is so extreme, the energy couples incredibly efficiently into kinetic shock waves instead of just dissipating as heat. A single teraton detonation creates what the source material perfectly describes as scalable earthquakes in the air.
That's a fascinating image. What's the physical size of that shock?
The initial fireball would be 90 to 110 miles in diameter, but the blast effects, the pressure wave itself, covers a radius of over 1,100 miles.
So when you realize the entire circumference of Venus is only about 23,000 miles, one of these detonations perturbs the dynamics of an entire hemisphere.
And the shockwave will circle the planet multiple times before it dissipates.
So the strategy isn't just to drop one big bomb. It has to be a carefully coordinated campaign.
Absolutely. The coordination is everything. The strategy dictates these detonation patterns at an altitude of 50 to 70 kilometers, which is right in the middle of the main cloud deck.
Why there?
That's the sweet spot where the energy couples most efficiently to the atmosphere's bulk motion. And they use coordinated waves of 10 simultaneous detonations.
And the goal of setting them all off at once.
It's to achieve constructive interference. Imagine two waves in a pond. If they hit each other trough to trough, they cancel out. But if the peaks of 10 different pressure waves are timed to arrive at the same location at the same nanosecond,
They add up. A super peak.
exactly, you generate these localized pressure spikes that reach 150% of the ambient pressure. And that triggers massive, unnatural convective instability. You're creating controlled, temporary superstorms just by focusing shock waves.
So the total energy budget for this campaign over 20 years is 2.5 times 10 to the 21st joules. And the goal isn't to just blow the atmosphere off.
No, that would take far more energy. The goal is to catalyze instability, to force this unnatural mixing, churn the atmosphere from top to bottom, and set the stage for the next set of systems to start picking off the loosened gases.
Okay, so if the mirrors are the continuous engine and the nukes are the violent episodic shocks, the next three systems are more like surgical tools.
That's a good way to think of it. They manage chemistry, they remove mass incrementally, and they organize the chaos into productive channels.
Let's start with System 3, kinetic bombardment. This sounds like pure brute force, but you're saying it's actually about chemistry.
It's a chemical engineering solution disguised as planetary artillery.
Yes.
We're firing tungsten penetrators. Each one is about 4 metric tons launched by massive railguns. And the speed is the key. 15 kilometers per second.
15 kilometers per second. That's about the speed the International Space Station orbits Earth, but you're directing it downwards.
And the energy release on impact is enormous. Each strike is like 108 tons of TNT. It creates craters about 150 meters across and 50 meters deep.
Okay, but here's the question. Why bother with this planetary machine gun, when you have Terraton nukes that can vaporize huge atmospheric volumes?
This is the chemical nugget. Venus's surface is heavily weathered. It's been sitting under a high-pressure, high-temperature co-Euro atmosphere for billions of years. So the reaction that you want to happen where co-Euro combines with calcium and magnesium silicates in the crust to form solid rock, a carbonate.
That reaction is thermodynamically favorable. It wants to happen.
It wants to happen, but it's kinetically limited. The weathered surface is like a layer of sealant. Nothing can get through.
Ah, so the bombardment is purely mechanical. It's just there to strip away that sealant layer.
Precisely. Each impact exposes about 750,000 cubic meters of fresh, unweathered silicate rock. And this fresh crust immediately starts reacting with that highly turbulent, co-rich atmosphere that's being constantly churned up by the nuclear shocks.
But even if it's super efficient on that fresh rock, does the scale of the campaign really make a dent in Venus's total atmospheric mass?
That's a very fair question. The source calculates a campaign of 1 million impacts over 50 years. That would sequester about 1.8 times 10 to the 14th kilograms of QRO. And you're right, that is only about 0.04% of the total atmospheric mass.
So it's a tiny fraction. It doesn't solve the problem on its own.
No, but its role is persistent chemical activity. Its importance is that it maintains a permanent active carbon sink. It stops the system from ever re-equilibrating chemically.
So it's always pulling CO2 out of the air, even if it's just a little bit at a time.
Exactly. And crucially, the impacts are timed. They're meant to coincide with the peaks of the nuclear-induced storms, maximizing the exposure of that fresh crust to the most violently mixed parts of the atmosphere.
That coordination again. Okay, that leads us to System 4, the high-energy laser arrays. The big chemical problem on Venus is that Kihaora is stable. It's fully oxidized. It's the end of the line. You can't burn it. How do the lasers get around that?
They get around it by brute forcing the kinetic limits using something called photochemical dissociation. The proposal calls for free electron lasers, each one delivering 100 megawatts of continuous output.
And this isn't just pointing a bright light at the planet.
No, not at all. The wavelength is precisely tuned to the 4.3 micrometer Kihaora absorption band.
So that's a specific frequency that makes the Ki molecule vibrate and stretch.
Exactly. You're injecting highly specific resonant energy directly into the CO bonds to rupture them. You are literally shattering the Kihaora molecule with targeted energy.
And that breaks it down into what?
Into carbon monoxide, CO, and highly reactive atomic oxygen radicals.
Now, those products will just want to recombine back into Cero, won't they?
They will, yes, and that's why the system needs constant energy input. But the temporary dissociation creates a volume of air that is highly enriched with these extremely reactive oxygen species. It preconditions the air.
What's the scale of this laser system?
We're talking about 50 orbital platforms generating a total continuous output of 20 gigawatts.
20 gigawatts. That's like the power demand of a major city.
It is. And when focused, these systems deliver power densities of 1 megawatt per square kilometer to selected atmospheric volumes. It's enough to drive significant dissociation.
So again, their role isn't mass removal, it's preparation.
Exactly. The lasers are used to precondition atmospheric volumes just ahead of the next wave of nuclear detonations. You enrich the air with reactive oxygen to enhance the fireball chemistry, and you also target the superheated polar regions.
The ones created by the mirrors.
Right, where the atmosphere is already thinned and hot, and escape velocities for those lighter oxygen atoms are more achievable. Again, every system feeds the next.
Okay, the final manipulation system is maybe the most speculative, but also the most novel. System 5, acoustic resonance weapons. We're talking about imposing structure on chaos, which seems counterintuitive when you're already churning the atmosphere with Terraton nukes and 1,000-mile-an-hour winds.
It does, but this system leverages the unique physics of Venus's atmosphere, primarily its sheer density. The speed of sound there is incredibly high, around 700 meters per second, and that dense high-velocity medium is perfect for transferring energy over planetary scales.
So what's the apparatus? What kind of orbital platform can generate sound waves big enough to affect a whole planet?
The platforms are massive. They use 500-meter diameter reciprocating pistons driven by powerful linear motors, and they generate extremely low frequency, or ELF, pressure waves between 0.1 and 1 hertz.
So these aren't sounds you can hear, they're just pressure oscillations.
Exactly. And the size of the resulting wave.
It must be huge.
The wavelengths are between 700 and 7,000 kilometers. The physical size of the wave approaches the circumference of the planet itself. We are literally, but very specifically, vibrating the entire planetary atmosphere.
How does that do anything besides just shaking the air around?
It exploits the principle of acoustic resonance. You know, every physical object, a bridge, a wine glass, a planetary atmosphere, has natural frequencies it likes to vibrate at. It's eigenfrequencies.
Okay.
Venus's fundamental atmospheric mode, its deepest resonant frequency, is around 0.2 millihertz. So by driving the atmosphere at or near these frequencies, you can use modest energy inputs to create significant planet-scale standing waves.
A standing wave, that's like when you shake a jump rope.
Yep.
Right. Certain points, the nodes stay still, and other points, the antinodes move the most.
That's a perfect metaphor. So think about it. The nuclear detonations create chaotic, turbulent mixing. Energy is going everywhere. The acoustic standing waves impose fixed spatial structure on that chaos. This is what the paper calls acoustic shepherding.
So the atmosphere is being violently churned, but the standing waves give that churn a direction.
Precisely. The standing waves create these fixed regions, the antinodes, where upwelling and intense vertical mixing dominate. It channels the hot reacting gases rapidly upwards towards the exobase. And at the same time, the nodes restrict motion in other areas. It funnels the energy.
So this is the organizational layer. If the mirror gradient is the engine and the nukes are the pistons providing the power, the acoustics are like the timing belt.
That's a great way to put it.
It makes sure the energy is delivered efficiently to the right place for atmospheric escape.
It transforms randomized turbulence into organized, productive circulation. And that's the final piece you need to achieve the cascade.
Okay, so now that we've laid out all 6 of these incredible interlocking systems, let's get to the timeline. This is where we see how Venus goes from stubbornly resisting this change to actively participating in its own collapse.
Right. This is the cascade in action.
Let's break the century into 3 acts. starting with years 0 to 30. Initiation and reaching what the paper calls the critical threshold.
So the first decade, years 0 to 10, that's purely infrastructure. It's orbital construction on a scale we've never seen before. The mirror array hits 50% deployment by year 10.
So you start getting those first measurable permanent polar gradients.
Exactly. You start that big meridional circulation. In parallel, the laser arrays, the railgun platforms, and all the nuclear devices are being built and positioned in orbit.
And the actual process, the initiation of the collapse, starts around year 10.
Yes. The first coordinated waves of the 10-gigaton devices detonate. That immediately triggers these massive, deep atmosphere convective systems. Kinetic bombardment begins, timing the impacts to hit right at the peak of these nuclear storms.
And the lasers are on, preconditioning the air.
Right. And then by year 15, the mirror deployment is complete. You have the full 1,500-degree gradient, and the sustained circulation accelerates to its peak of 500 meters per second.
So the first couple of decades are really all about setting the stage. What is the measurable result that defines that year 30 critical threshold?
By year 30, the atmosphere is permanently perturbed. It cannot go back. The storm systems created by the shock waves are now continuous. They don't decay back into the old superrotation model.
But there's a key metric, right?
The most critical metric is atmospheric escape flux. The rate at which the atmosphere is physically being ejected from Venus's gravity well exceeds 100 kilograms per second.
100 kilograms a second. How does that compare to the natural rate of atmospheric loss?
It's about 50 times the natural rate, which is only about 2 kilograms per second. At this point, the transformation becomes mathematically self-sustaining. The energy you're losing through escape is now greater than the energy required to maintain the forcing. Venus is past the thermodynamic point of no return.
That's the moment.
Oh.
The moment the planet flips from resisting the change to embracing it.
Okay, let's move into the longest and most important phase. Years 30 through 80, the sustained and accelerated cascade. This is where you see the immediate escalation of the forcing. The nuclear campaigns shift dramatically from the 10-gigaton devices up to the 100-gigaton devices. You're maintaining a much higher baseline of atmospheric churning.
And the acoustic weapons come online.
They activate periodically, imposing that critical spatial structure on the chaos, efficiently channeling all that energy up toward the escape pathway.
And the physical evidence of cooling must become really tangible during this phase.
Oh, absolutely. The polar cold trap grows substantially. By year 40, you have permanent ice caps of solid Kyoto that extend all the way down to 40 degrees latitude. This is atmosphere being physically removed and sequestered as a solid.
You mentioned a critical transition around year 65, where a positive feedback loop kicks in. What causes that?
So as the pressure drops below 70 bars, the thinning atmosphere does two things. First, it lets the energy you're injecting couple even more efficiently. But second, and this is more important, you cross a threshold where non-thermal loss mechanisms become dominant. We're talking about Jean's escape.
Can you just quickly clarify Jean's escape for us?
Sure, it's the loss of gas from the very top of the atmosphere, the exobase. If a molecule up there gets enough energy from heat or a collision to reach a velocity greater than the planet's escape velocity, it just drifts away into space.
And because Venus's gravity is a bit lower than Earth's,
and the molecules are already incredibly energetic from all the heating, as soon as the atmosphere thins enough for that heat to reach the exobase efficiently, the escape rate of Koyuro and its parts just accelerates dramatically.
So it's a virtuous cycle of destruction. Less atmospheric mass makes it easier to heat the remaining atmosphere,
which increases the temperature and velocity at the exobase.
which increases the escape rate, which reduces the mass even more, making it even easier to heat.
A textbook positive feedback loop. It accelerates the collapse exponentially. The escape flux skyrockets, hitting over 500 kilograms per second by year 70. And this period is also punctuated by the most dramatic events of the whole campaign, the introduction of the Terraton scale devices between years 60 and 80.
So the Terraton shocks are no longer just for initiation, they're for maintenance.
They're to ensure that these far from equilibrium dynamics are permanently maintained. The shock waves circle the planet, creating sustained atmospheric waves that just prevent any chance of the system settling back down.
And all this time, the quiet work of the kinetic bombardment is creating a truly massive carbon sink on the surface.
It's relentless. By year 75, something like 5% of Venus's entire surface consists of fresh crater floors and walls, all less than 50 years old. This maintains an active carbonation rate far, far higher than what's possible on the old weathered crust.
So after 80 years of this completely synchronized, multi-pronged assault, What's the first major result that an average person could look at and say, okay, this is working?
By year 80, the global average surface temperature has dropped by 50 degrees Celsius, down to about 400 degrees. Now, that's still uninhabitable, of course,
Of course.
but it demonstrates a decisive break in the planet's long-standing energy budget. The greenhouse runaway reversal has, at that point, conclusively begun.
Which sets the stage for the final push. Years 80 to 100, the final approach.
And now the transformation really accelerates because the atmosphere is so much thinner. The supercritical region, that weird altitude where Kyo isn't really a gas or a liquid, it shrinks dramatically from 30 kilometers altitude down to about 10. The whole structure of the atmosphere changes.
And the pressure must drop very quickly now.
It does. It continues to decline steeply, reaching about 50 bars by year 100. That's a 45% reduction from the initial 92 bars. You now have an atmosphere with less than half its initial mass. It's a profoundly different planet.
Let's just review the final numbers on mass removal. Did the engineering actually work out?
Yes, the numbers align very closely, and it really shows why you need all the systems working together. The total escape loss over the century from genes escape and other mechanisms is about 0.4% of the initial mass. But then crustal sequestration from the impacts accounts for another huge chunk, and the polar ice caps sequester another 5 times 10 to the 11th kilograms.
So the solid phase removal really matters.
It's essential. It shows the viability of the whole coordinated approach.
And the final temperature drop after a full century of this relentless forcing.
By year 100, the global average surface temperature is down to about 320 degrees Celsius. That's a 130 degrees Celsius decrease overall.
Okay, so what does this all mean? We end up with a planet at 50 bars and 320 degrees Celsius that is nowhere near Earth habitable. Does that mean the 100-year campaign was a failure?
Absolutely not, because by year 100, Venus is profoundly and permanently altered. The goal was never habitability in a century. The goal was thermodynamic reversal.
Yeah.
The new atmospheric dynamics, the permanent polar circulation, the sustained escape flux, the established carbon sink, they all persist in a self-sustaining form. The planet cannot go back to its initial hostile greenhouse state. The critical work is done, the heavy lifting is complete, and the foundation is set for the next phase.
So the physics problem is solved. But this transition from a stable hell to a reversible hell in 1 century now becomes the single largest industrial and logistical undertaking humanity has ever even imagined. Let's just look at the resource requirements for the energy involved.
The material inputs are, well, they're astronomical. For the nuclear campaign, you need massive amounts of deuterium from water and tritium bred from lithium for the fusion fuel. Then you look at the kinetic systems. You need 4 million metric tons of tungsten for the penetrators.
4 million metric tons of tungsten. That's a staggering amount of a very specific metal. Where do you even get that?
It requires a focused, sustained campaign of asteroid mining, specifically M-type metallic asteroids, which are rich in heavy metals like nickel, iron, and tungsten.
So this isn't just grabbing a few rocks. This is building an entire space-based heavy industry just to feed the railguns.
That's right. The source estimates you'd need to process about 50 million metric tons of asteroid material to get the refined tungsten you need.
Okay, what about the orbital infrastructure itself? The mirrors, the platforms, those giant acoustic drivers. How much mass are we launching?
The total orbital infrastructure, all the railguns, the lasers, the acoustic platforms, it totals about 400,000 metric tons.
400,000. To put that in perspective for you listening, the entire International Space Station weighs about 450 metric tons.
So we're talking about launching the mass equivalent of nearly 900 international space stations.
That's immense. And that's where ambition usually crashes into the reality of the launch budget. How do we get 400,000 tons out of Earth's gravity well and into orbit around Venus?
This is where the plan becomes surprisingly grounded. If we assume a realistic, modern, heavy lift capability, say 100 metric tons to low Earth orbit per launch, which reusable boosters are getting close to, that 400,000-ton requirement translates to 4,000 launches.
4,000 launches. And you have to do that over the critical 20-year construction and deployment period. So that averages out to 200 launches per year.
And here's the crucial part. 200 launches per year is comparable to the current total global launch rate when you factor in every country, every private entity.
So it's not technologically infeasible. It just requires a sustained, coordinated global effort.
It's an order of magnitude increase in focus, not an order of magnitude increase in technology.
Let's talk about the money. What's the dollar cost of engineering an entire planet?
Well, if we assume launch costs come down because of reusability and economies of scale, the total launch cost is estimated around $400 billion. Then you add in all the orbital fabrication, R&D for the Terraton devices, the asteroid mining infrastructure. You're pushing the total program cost toward $1 trillion over the 100-year timeline.
$1 trillion over a century. That number sounds huge, but let's put it in context. What is that annually?
Amortized, it's about $10 billion a year. And when you compare that to the current global GDP, it's roughly 0.1%.
Let me give you a historical contrast. The Apollo program, just to land a man on the moon, peaked at about 4% of the U.S. GDP in the 1960s.
It's a powerful comparison, isn't it?
It is. We're talking about achieving planetary transformation for 1/40th of the economic strain the U.S. took on to get to the moon 50 years ago. The money is clearly within reach.
So the limiting factor isn't the tech or the total cost. It's the sustained political and industrial will.
But engineering on this scale carries immense risk. If you're using extinction-level energy and forcing a thermodynamic collapse, what does the risk assessment look like?
The risks are categorized into technical failures and systemic failures. Technical failures like a nuke going off in the wrong place or a big failure in the mirror system, those are mitigated through massive redundancy and real-time atmospheric modeling. You just assume some parts will fail.
But what's the single biggest systemic risk? The catastrophic worst-case scenario.
That would be the systemic cascade runaway risk. The transformation just accelerates beyond our control. If that positive feedback loop we discussed becomes too violent, you could see Venus transition too rapidly toward being an airless or frozen planet, skipping the manageable transition period entirely.
How do you even modulate that when you're dealing with forces that are literally planetary in scale?
Through adaptive control. The whole system is designed with sophisticated real-time monitoring. So if the escape flux goes above, say, 1,000 kilograms per second, twice the maximum predicted rate, the continuous forcing systems, like the mirror intensity and the lasers, have to modulate immediately to slow the cascade down.
You just turn down the heat and the wind.
Exactly. You restore control over the rate of collapse.
And finally, the human factor. Political risk. A century of sustained political will, especially with a $1 trillion budget. That's hard to guarantee in our world.
This is probably the most pragmatic part of the whole design. The proposal addresses that political volatility by front-loading the infrastructure.
Meaning you build everything you can at the beginning.
Right. The goal is to minimize the ongoing operational needs once the systems are deployed. So by year 20, the major pieces, the mirrors, the railguns, and importantly, all the nuclear devices, are already built and pre-positioned in stable orbits for later use.
And this allows for what the paper calls graceful degradation.
Yes. Even if political will completely falls apart after that initial 20-year build-out, the deployed infrastructure ensures that the transformation continues on its own because of the self-sustaining nature of the cascade. The planet can't go back. The hard work is already done.
What an incredible survey of ambition, of physics, and just sheer industrial coordination.
Yeah.
We started with Venus as this hostile, stable giant. And I think the central takeaway is that this transformation relies entirely on systematic coordination. It's about exploiting thermodynamic sensitivity, not just brute force.
That's it, exactly. Every single system, the Terraton nukes giving you the chaotic shocks, the kinetic bombardment giving you the chemical sink, the lasers preconditioning the air, the massive gradient creating the engine, and the acoustic shepherding imposing structure, each one amplifies all the others multiplicatively. That's the real genius of the cascade engineering model.
It transforms what would be a 1,000-year wait into a century-long, active, monitored intervention. It sets the foundation for true habitability in the centuries that follow. By year 100, we've successfully reversed the greenhouse runaway. The planet is on a path where surface pressure will eventually approach 10 bars and temperatures around 150 degrees Celsius over the long term.
By the time that first century closes, we would have a planet that is profoundly altered and permanently launched onto a new evolutionary path. The evening star, yielding not slowly, but decisively to human ambition and engineering.
And that leads us to our final provocative thought for you to chew on. The techniques developed for this Venus campaign, the scaled orbital mirrors, the Terraton-scale nuclear devices, the precision acoustic drivers, they don't stop at Venus.
No, they represent a universal toolkit for macro engineering. Mars terraforming could use similar mirror arrays to control the climate. Gaining access to the oceans of Europa might involve kinetic penetrators and carefully scaled nuclear devices to breach the ice shell. It's all based on the same principles of controlled perturbation.
So the ultimate proof of concept here is that if Venus, the most thermodynamically challenging body in our inner solar system, can be transformed in a mere century by industrial coordination.
The no planetary environment in the solar system remains beyond our engineering reach. The transformed Venus becomes the morning star of a fundamentally and irreversibly transformed solar system.
Welcome to The Debate. Our focus today is on an undertaking that feels less like engineering and more like planetary warfare. We're talking about the proposed effort to terraform Venus, to fundamentally transform its surface environment, 450 degrees Celsius, 92 bars of CO2, into a proto-habitable world, and all within a single century.
Right.
Now, the central question, I think, isn't really about whether we possess the raw energy to do this. It's about control. The proposed methodology is this: cascade engineering model, which relies on the complex, synchronized action of 6 high-energy systems. We're talking orbital mirrors, lasers, kinetic bombardment, theoretical acoustic weapons, and even Terraton-scale thermonuclear devices.
And the sheer audacity of trying to coordinate those systems across an entire planet is, well, it's what gives me pause.
Absolutely. So the question is this: is this strategy of creating and managing global non-equilibrium dynamics, essentially forcing a stable planet to constantly tear itself apart, is that a sound engineering approach grounded in predictable physics? Or does this reliance on unprecedented scale and complex synergy introduce a fundamentally unpredictable model is inherently sound? It's sound because it meticulously leverages known, scalable physics, from Taylor-Ulam energy scaling right down to basic
That no adaptive control system, no matter how sophisticated, can reliably mitigate.
Okay, well, let's start with the foundation of my position. The core mechanism. You can think of them as these massive, continuous pole-to-pole superwinds, circulating at over 500 meters per second.
A speed that would, it would literally tear.
Energy inputs, the lasers, the Terraton devices, feasible and targeted. They're simply nudging an already unstable system in the direction we want it to go. That is the energy release equivalent to an extinction-level event on Earth, and here it's specifically directed to catalyze atmospheric instability. This isn't about heating. It is about controlled destruction.
Controlled destruction. That's a perfect phrase for the ambition, if not the technical certainty.
And the model guarantees equilibrium state and the sustained atmospheric escape flux, so the rate at which we lose atmosphere to space is above 100 kilograms per second. This rapid confirmation
is inherently fragile. The entire success concept is predicated on 6 massive, complex, and highly theoretical systems. One system compromises the forcing conditions required by the others. You mentioned the theoretical components. Okay, take the acoustic resonance weapon at a planetary scale.
But they are designed to exploit known atmospheric eigenfrequencies.
Perhaps. But then look at the systems that are proven, like kinetic bombardment. The plan calls for 1 million impacts over 50 years. That's an immense logistical endeavor, yet it only sequesters 0.04% of the total atmospheric mass. Its role is, well, it's highly marginal in the overall mass balance.
With the kinetic bombardment is catalytic. It exposes fresh crust that reacts chemically with the atmosphere. It's not a primary mechanism for mass removal.
Exactly my point. It requires perfect synergy with the atmospheric chemistry that's initiated by the lasers just to justify its immense logistical footprint. And speaking of footprint, the risk assessment is wildly optimistic regarding infrastructure. Building the required orbital infrastructure means launching 400,000 metric tons of material. That's 4,000 heavy lift market launches over 2 decades. It's easy to throw around figures like that and forget that we are talking about creating a city in orbit just to start the job. That level of complexity introduces failure points that can easily derail a 100-year project before we even fire the first Terraton device.
Okay, we need to address that interplay directly, because this is contention 1, the reliability of synergy versus the introduction of chaotic dynamics. You suggest that this complex mixing is inherently unreliable, but I'd argue that the synergy is entirely predictable, precisely because specific systems precondition the atmosphere for the following step.
I appreciate the idea of preconditioning, but I think you're confusing a theoretical model with engineering reality here.
Well, consider the high-energy lasers. They deliver 20 gigawatts of continuous output, precisely tuned to break the chemical bonds in CO2. These lasers create a reactive soup of oxygen radicals ahead of the nuclear detonations, which enhances the efficiency of the fireball chemistry. This is highly tailored atmospheric chemistry, not some arbitrary chaos.
That sounds nice on paper, but I'm not convinced by that line of reasoning. You're staking the success of the most volatile energy system on the perfect functioning of a highly complex chemical pretreatment system. You're assuming that 20 gigawatts of laser power focused on a turbulent, dense, chemically reactive atmosphere can guarantee the dissociation of CO2 without creating new, unforeseen feedback pathways or exotic chemical species. The atmosphere is an enormously complex reactor, and you are introducing massive amounts of radicals. Are we really sure the outcome strictly follows your intended pathway?
But the goal is just to exceed the local chemical equilibrium concentration, creating metastable states that enhance the subsequent reaction efficiency. It doesn't need to be perfect, it just needs to be better than baseline.
And what about the acoustic system? We're talking about utilizing atmospheric eigenfrequencies, the natural humming note of the entire planet, with massive pistons to create standing waves across the globe. This isn't just risky, it risks exciting destructive or, counterproductive resonance modes. If those planetary standing waves interact negatively with the multi-month shock waves from the teraton-scale detonations, you are not organizing chaos. You are risking large-scale destructive pressure wave interference, which could undermine the very thermal gradient stability the mirrors are supposed to create.
That brings us directly to contention 2, the necessity and inherent risk of the teraton-scale nuclear forcing. You highlight the cost and logistical risk, but the teraton scale is fundamentally necessary for the sustained cascade dynamics we need.
But why must it be that big?
Because of the energy coupling in Venus's dense atmosphere, a single 1 teraton device creates hemispheric-atmospheric shock waves. The source material calls them true planetary earthquakes in the air that persist for months. This persistence, this sustained atmospheric stirring, is the only thing that maintains the perturbation required to prevent the atmosphere from settling back into equilibrium. The total nuclear campaign, 2.5 times 10 to the 21st joules, delivered over 20 years, is essential for rapid vertical mixing and thermal transfer.
I understand the persistence benefit of a larger shockwave, but the necessity of escalating to yields in the 10 to the 22nd joule range is the questionable leap. If the goal is catalyzing instability, not direct bulk heating, does the marginal benefit of a slightly more persistent shockwave really outweigh the astronomical engineering and logistical risk? We're talking about deploying and coordinating devices that mass several thousand metric tons each.
The financial cost, yes, it's estimated at $1 trillion for the entire program, which is significant, but it's amortized over a century. That's a manageable investment for a world.
The financial argument is one thing, but it's secondary to the political one. This high-visibility, high-risk nuclear system is the single largest point of failure, not just technically, but politically. The source material itself identifies interruption due to instability or shifting global priorities as a serious non-technical risk. Deploying hundreds of teraton-scale devices over decades makes this entire venture highly vulnerable to shifts in global commitment, jeopardizing the whole 100-year timeline. I'm just not convinced that we couldn't achieve sufficient perturbation using more frequent, smaller devices and dramatically lower the barrier to entry and the overall systemic risk.
But smaller devices do not couple energy effectively enough in the dense lower atmosphere to achieve that necessary months-long perturbation window. The physics suggests that to get that permanent shift away from equilibrium, we need the shockwave persistence that only the teraton scale can provide. The model is optimized for maximum sustained impact per unit of operational time.
But optimization for maximum impact often comes at the cost of robustness and grace and failure.
Which brings us to our final contention, managing systemic cascade runaway and adaptive control. You implied earlier that these nonlinear dynamics could lead the process to run away. I would argue the system is meticulously designed for adaptive control, and the risk of catastrophic runaway like transitioning too rapidly to an airless or frozen state is minimal.
Minimal based on idealized modeling, maybe.
Minimal because the atmospheric mass reservoir is enormous. It provides a massive thermal and physical inertia. The plan specifically accounts for accelerating loss. If the escape flux exceeds the maximum predicted rate of 1,000 kilograms per second, the control loop immediately mandates reducing mirror intensity, slowing the thermal gradient, and modulating the nuclear detonation frequency. We have powerful levers to throttle the energy inputs. The system is engineered for graceful degradation, not for an immediate collapse.
That is a compelling argument regarding the levers. But the key issue is the speed of the feedback, particularly during the accelerating phase. Let's say years 60 to 80. The model itself notes that when pressure drops below 70 bars, genes' escape of CO2 becomes significant. This creates a powerful positive feedback loop. Reduced mass leads to higher high-altitude temperatures, which leads to higher escape flux, which further reduces the mass.
But that feedback is the desired phase transition.
It is, but the goal is controlled acceleration. The time constants for modulating the massive mirror array, which is 200,000 metric tons of reflective material, or adjusting the complex prepositioned nuclear cadence may be too slow to halt an unforeseen superacceleration once the system crosses these nonlinear critical thresholds. You can't just stop a planetary-scale positive feedback loop instantly by flicking a switch. We might overshoot the targeted habitable parameters, potentially stripping the atmosphere too far, or forcing a premature condensation of CO2 into permanent polar caps, creating a frozen rather than habitable world.
The control system involves reducing the 3.5 times 10 to the 17 watts of intercepted power from the mirrors. That is the largest lever, and the sheer inertia of the atmospheric mass buys us years, not seconds, for the mirror configuration to adjust. While the transformation is profound, the percentage of mass loss required to reach the target is still relatively low, minimizing that runaway risk.
That relies on perfect predictive modeling for when those nonlinear thresholds are crossed. And I maintain that projecting the synchronized multiplicative effect of 6 massive volatile systems into the future, particularly when the atmosphere is in a state of permanent non-equilibrium, well, it's a level of certainty our current physics and engineering simply cannot guarantee. The system is too complex and too volatile to promise control.
So, to summarize, we have established that the Cascade model offers a theoretically credible pathway to profound planetary alteration within a century. By exploiting Venus's inherent thermodynamic sensitivity through continuous thermal forcing from the mirrors and episodic high-energy inputs from the Pterodon devices, the transformation shifts from passive resistance to self-sustaining dynamics. This results in a system where the CO2 atmosphere cannot re-equilibrate, guaranteeing the necessary surface pressure of 50 bars and a temperature of 320 degrees Celsius by year 100. It is a highly demanding, but ultimately tractable engineering symphony.
But the certainty claimed for this approach is, in my view, dubious. The entire project's success hinges on the synchronized multiplicative cooperation of 6 complex systems, pushing the limits of physics with Terraton scaling and the limits of control with acoustic resonance systems. While the foundational physical principles are sound, the model fundamentally underestimates the intrinsic fragility and the potential for catastrophic, non-recoverable failure when attempting to manage planetary-scale chaos. This leaves the entire 100-year transformation highly vulnerable to technical surprises and, of course, political instability.
I think the material underscores that while planetary environments are certainly not indefinitely locked in their current states, the path to reshaping a world like Venus involves engineering demands and coordinated risk that really do push the boundaries of current technological certainty.
A test of certainty that may hold unacceptable risks if the complexity exceeds our capacity for prediction.